Hello again. Let me welcome you to the section M2 Modeling and Simulation of Climbing and Walking Robots 2. In this section, we will have four interesting presentations. We will start with the first one, analysis of passive dynamic gait of Tensegrity robot. And I ask Fumihiko to share the screen. I think Fumihiko is there. Are you there, Fumihiko? It's the first speaker.
Excuse me, I'm the first speaker, but I'm not Fumihiko.
Okay, so I'm sorry. I apologize. So can you please share your screen?
Okay. Hello everyone. It's my pleasure to introduce our new research about the Tensegrity robot. I'm Zheng Yanqiu, who comes from Japan Advanced Institute of Science and Technology. I will start with the word Tensegrity, which comes from the composition of tensile and integrity, was proposed in the construction industry in the last century, as shown in this figure. It is composed of several compression and tension elements, which is bars and ropes. The advantages of this structure are obvious. This structure can be very light, however, it is very strong. With the feature of softer material, it has a high resistance to external forces, and most importantly, it can be transformed into many shapes depending on the connection relationship and the length of the ropes. And our human movement system, meaning consists of bones and muscles. Such a structure can protect the joints by distributing the force to the muscles when subjected to external forces. So the Tensegrity structure can be fully similar to the human movement system and has the same advantages over rigid robots. Therefore, the research on Tensegrity joints and the Tensegrity robots has gradually increased in recent years. Since the Tensegrity structure has so many advantages, why is it not widely used? It is necessary to introduce the disadvantages of Tensegrity structures, which is complex. The main ones are connection method and dynamics modeling. Therefore, many studies on the locomotion of Tensegrity robots avoid the dynamics model. For example, by using mechanical learning methods or have used static modeling. It often leads to difficulty in analyzing the forces on the robot and cannot use model-based control, which make the robot's speed accuracy are not high and thus cannot be widely used. So, our research focus on this problem. For complex connection, we use the idea of splitting the complex problems into multiple simple problems to find the simplest model that can be splitted out. Second, for the dynamics modeling of the Tensegrity robot, we are inspired by the rimless wheel, which is widely used as one of the basic models of robot walking. Based on this, we propose the subject of this study, the passive working of the Tensegrity robot based on the minimal model. We believe our research can provide a mathematical theory not only for the application of Tensegrity robots, but also a new idea for modeling in software robots. According to the passive working theory of rimless wheel, when the angle between two legs is less than 90 degrees, the energy loss due to collision will not be zero after one step is. So, we propose a model that consists of 3 lamps and 6 temples. Such a structure ensures that the angle between the leg is 60 degrees. During the robot motion, not only single line support but also double line support will occur. So we give corresponding equations of motions based on different states of motion respectively. Here, the generalized coordinate vector represents that the system is composed of 3 lamps independently of each other. And this system is mainly composed of concentric forces, which is support forces and elastic forces. In the case of double line support phase, in the case of a single line support, we assume that the connect point to the ground in lamp B will not slide on the ground. So the constraint is that the velocity of the connect point is 0. Then the constraint Jacobian matrix can be written as this. And when supported by 2 lamps, we assume that the lamp A and B connect on the ground in the same time. So the constraint matrix of Jacobian are this. By associating the equations of motion and the constraint conditions, we can obtain the condition force, which is support force on the ground. Therefore, we can get the constraint force for single line support and double line support, respectively. Here, X is defined as this. Because Jacobian matrix JA and JB are showing respectively, so the result of XAB and XBA is equal to 0. Then the constraint force or support force in the case of double line support is shown in this formula. We can find that this is consistent with single line support, so we can give the conclusion that it can be shown constraint force of each lamp is independent of each other, whether it is single line support or double line support. The elastic force vector is shown in this formula, which is composed of the tension force generated by 6 cables, and here we take one of the cable as an example to analyze it specifically. As shown in this figure, the tension of cable acts at 2 connected points, where JAC represents the Jacobian matrix at the point AC, while F1 is the magnitude of the tension, and DAC-BC is the direction of the tension. And the magnitude of the tension we use the spring damper system to represent. Here, LS is the length at the equilibrium point. That is, the cable can be adjusted by LS to define the tightness. We also assume an inelastic collision model to calculate the initial state of the next step after the end of one step. We use positive and negative subscript to represent the before and after collision. Using physical parameter in this list, numerical simulation by using MATLAB of a typical passive dynamic working gait is generated as shown in this slide. As located in the light purple ring, the velocity of lamp C keep varying while lamps A and B are fixed in the double line support phase. Once the velocity of the lamp varies, the single line support phase starts. Here, successful passive dynamic working gait can be achieved if the 2 principles to be obeyed. First, from double lamp support to single lamp support, the vertical ground reaction force of the nearing lamp decreases to 0, while the front one remains positive. Second, from single line support to collision, the vertical ground reaction force keeps positive, and the kinetic energy enables the center of the mass to overcome the position barriers. Let the robot works on the slope at any initial speed. We record it from 40 to 50 steps because the step period had converged, and then we get the phase plan plot like this, and can be seen the limit circle gait is achieved. Here, we change the position of the connection point between the cable and the lamp. That the range is from 0 to half of capital L to explore the effect of L. Then we get a result like this. As shown in this figure, we can see that no matter what the angle of the slope is, the step period of the robot tends to be the minimum when the distance of connection point is around 0.1. That is the midpoint of its range of change. Moreover, as the slope changes, exists a slope that causes the robot to move at the maximum speed, which is phi equal to 0.8. As the slope increased to 0.9, however, the robot showed a chaotic gait that we can see the step period tends to a new curve, indicating that the robot is realizing a new limit circle, which only needs a longer convergence time. This indicates that the potential energy of each step cannot be completed, consumed by collision, because by the elastic elements, part of the energy is converted into the elastic potential energy inside the robot. Consequently, the rest of energy will have remained for the next step, so that the chaotic gate has appeared. This also indicates that there is an upper limit to the energy lost by the robot due to the collision, which is one of the features of the robot itself, and also will explain the feature of the collision resistance of the Tensegrity structure. To investigate the convergency rate to limit circle of robot's gait, we obtain this figure. By changing the elastic element of the robot, the color of each point on the figure represents the number of steps taken by the robot gait to converge to the limit circle. The place where there are no dots represents the failure of working. First of all, it can be seen that with the increase of slope, the total number of points where the stable limit circle gate could be generated gradually increases. Next, when dumping coefficient C is small, an increase in elastic coefficient K has a positive effect on the convergency rate. This figure is demonstrative that the effect of elasticity on the variance of step period in 50 steps. The places where there are no points represents the robot falling down, and the color of each point represents the variance of step periods in 50 steps. Then we can observe the points with the values in the range of 0 to 0.05. We can see that even if the robot appears a chaotic gate, its chaotic degree is extremely small. In addition, the variance of most points is fully small, which shows that the Tensegrity robot can better achieve the limit circle. The points at the edge represents a large variance, which indicates that most of the chaotic gate will appear before the robot falls. Based on the above conclusion that the Tensegrity robot can better achieve the limit circle gate, we wonder if the elastic elements of the robot are not unified. Will the robot show chaotic gate or chaotic gate? We change 6 cables with the same elasticity coefficient K, that every elasticity coefficient of cables is equal to 1000, so that their variance is equal to 0. Then gradually increase the variance of the elasticity coefficients of the 6 cables to increase their variance from 0 to 200, and record the date from step 30 to step 60. From
Can you
this
please
figure,
jump to the
expressly,
conclusion, please?
the point of step period is all over this rigid robot, and introduce a mathematical method about modeling of Tensegrity robot. The numerical simulations are performed for limit circle gate generation and analyzed. And we also show the effect of elastic elements on gate, and find an interesting phenomenon that the Tensegrity robot will not appear chaotic gate by inconsistent elastic elements. And the chaotic gate was also observed. However, the reason is not clear, so that in future work, the chaotic phenomenon will be considered, and its effect on gate will be analyzed. Finally, if anyone is interested in our research or has questions, please feel free to send me an email. Thank you.
Okay, thank you very much for your presentation. Is there any question from the audience?
Excuse me. Yeah. I would like to ask how can this robot be used in the real environment through the simulation results?
All right. First, I'll say the Tensegrity robots are worthy of being used in space exploration or rescue because of their high adaptability. So in this paper, we are focusing on theoretical research, which can provide a mathematical method for modeling of dynamics of Tensegrity robots. And it can verify that the Tensegrity is more adaptable to the environment. So with our theoretical approach, the speed and accuracy of the Tensegrity robot can be made harder or and more valuable to be applied. Thank you.
Any other question? Okay, so thank you, Yanqiu, for your presentation.